Good day, Ma'am Ortiz. We are the Group 6 of CPE 115L from A22. And I'm Angeli James A. Velasco together with my group mates, James Samuel A. Judy, Caitlin Gilsey Morales, Ian Gabriel Esras, and Nerissa Dene Aitan Hueco. And our project is a 99-second stopwatch or timer circuit using decoders, counters, and 7-segment display. The project's goal is to use the notion of digital logic gates and the K-map to design and simulate combinational circuit. By constructing the project, we have a better understanding of each types of fundamentals operation as well its implementation. More importantly, we the researcher recognizes the value of combining circuit subtypes, developing more cost-effective technologies because it reduces the number of gates and wires, resulting in lower circuit complexity. The project contains components that are important and relevant to the main function and objective of the project. Components of the following such as decoder, counter, binary counter, decade counter, 7-segment display, and the cathode 7-segment display. And each component is important in completely functioning the whole circuit or the logic diagram, where each different type or category of the components are specifically used. Mr. James Samuel A. Judy will be discussing the project statement and its objective.
Good morning, ma'am. I'm James Samuel A. Judy and I'll be stating the project statement as well as the project objectives. So for the overview of the project, it is a 2-digit timer or stopwatch that automatically resets after counting from 0 to 99. The timer has reset, reverse, and pause functions. So for our objectives, the project is to apply the knowledge in decoders and counters as main components in creating a 7-segment display circuit, to understand and explain how the created 2-digit 99-second timer or stopwatch using decoder and counter works, and to use National Instruments Multisim as main logical diagram simulator. Caitlin Gail Morales will discuss the preliminary design for the circuit diagram.
I am Caitlin Gail Morales, and I will be discussing the preliminary design of our circuit. So in order to achieve the objective of this project, first, the state table, together with the state diagram and truth table of the 7490 and 7447 IC was completed. As you can see here in our block diagram, we have two 7-segment display that is connected to the two 7447 and decoder. The decoders are then connected to the 74 LS190D decade counter. Then below, we have 3 switches that can manipulate the counting process of the circuit. So next will be Ian Ras to explain the components used in the circuit.
Good day, ma'am. My name is Ian Gabriel Esras and I'm here to discuss about the components used in our project. In our project, the 5 main components used are the common cathode 7-segment display, the 74 LS190D counter, the 7447N decoder, the function generator, and the SPDT switches. For our first component to be discussed is the 7-segment display decoder. A 7-segment display decoder is a combinational circuit that uses a decoder to convert binary data into a decimal numbers. The logic gates in this decoder evaluates the incoming signal and switch on the segments accordingly. One particular configuration of the 7-segment display used in our project is the common cathode 7-segment display. The common cathode 7-segment display is a 7-segment display in which all the cathode LEDs of the LEDs are wired together. The next component, which is the 74LS190D IC, is a synchronous up and down BCD decade counter. Its state changes of the counters are synchronous with the low to high transition of the clock pulse input. It also contains 4 master-slave flip-flops together with several logic gates. Here is the respective diagram for our IC, which is the 74LS190D that is used in our project.
The second to the last component to be discussed is the 7447 and decoder. The 7447N IC is a BCD to 7 segment display decoder, and it takes BCD input from the 74LS190D counter and then creates the 7 output lines for the 7 segment display. Each input combination of the BCD is translated to its corresponding numeral display.
So next we have the function generator. The function generator is a special type of signal generator that can produce different types of waveforms, such as sine, square, and triangular waves for its output signal. The frequencies of the waveforms can be adjusted from a fraction of a hertz to several hundreds of kilohertz. Shown is the symbol for the function generator and its interface where you can change the type and frequency of the waveform produced. So next we will explain how the circuit works. First, in the function generator will supply a signal of 1 Hz to the clock input of one of the 74 LS190D counter. From this signal, the 74 LS190D decade counter will be producing a 4-bit binary coded decimal output in its 3, 2, 6, and 7 pins. But this BCD output cannot yet drive the 7-segment display. So the 7447 decoder will convert the binary code into a 7-segment code that will be shown in the 7-segment display. The count up, down, reset, and pause functions can be applied to the circuit with their corresponding switches. The switches allows users to switch from logic high and logic low. So the switch 1 is for reversing the direction of the counting, switch 2 is for the reset option, and lastly, switch 3 is for pausing the counting process.
Good day, so I am Nerissa Dani Aitanweco and I will be discussing the truth table of the 7447 IC and the state table of the 7490 IC. So for the truth table of the BCD to 7-segment decoder, it can be observed that the input values of BI prime slash RBO prime, RBI prime, and LT prime are on logic state 1 to enable the 7447 IC to deliver the desired output, which is to have output functions of 0 to 9 transferred to the inputs of the 7-segment display. Since the 7447 IC features active low outputs, the values of each pin should be in logic 0 to have an output of 1 in order to drive each of the respective segments in the 7-segment display to high, since the required input for a common cathode display should be high. Next would be the state tables for the up and down BCD counter. Since the valid values for a BCD counter only ranges from 0 to 9, the inputs and outputs for values 1010 to 1111 is set to don't care condition. An up and down BCD decade counter has two conditions: when count control M is equals to 0 and M is equals to 1. When M is equals to 0, the counting direction is upward through any given count sequence. On the other hand, when M is equals to 1, the counter will start counting downwards. Q sub 0 is the least significant bit of the BCD decade counter. When the circuit is in up count control, the output for the present state values 0000 to 1000 is set to low and changes to high when the present state is 1001 in order to enable the count of the next higher significant decade, which is Q sub 1. On the other hand, when it is on down count control, output is set to high when the present state is equals to 0000, since its next state 1001 would reset the counting sequence and consequently enable the down counting of the next higher significant decade Q sub 1. As for the state table of the Q sub 1, it does not have any output since there is no higher significant decade connected next to it. So this is the state diagram of the up and down BCD counter, wherein the concept of this type of counter is further illustrated with the blue arrow signifying the direction of an up count, while the red arrows signify the down counting of the counter.
So for the simulation of our circuit project, it will be divided into three parts as the circuit has three switches to be toggled. So for the first part of the simulation, the switch 1 is connected to the ground and the circuit shall display a counting sequence, upward counting sequence. So let's try it. As you can see, with switch 1 connected to the ground and switch 2 connected to the voltage supply and switch 3 connected also to the ground, the circuit will count upwards. And as we toggle the switch 1, the circuit will now count downward because it is now connected to the voltage supply. So for the second part of the simulation, the reset switch acts as a reset that the circuit will reset its counting if toggled into the ground. So let's try it. As you can see, the circuit stops its counting since the switch 2 is now connected to the ground. For the third part of the simulation, the pause function or the pause switch will act as the pause or the start of the circuit. With switch 3 connected to the ground, the circuit continues to count downward because of the switch 1 connected to the voltage supply. And as we toggle the switch 3, it will pause or temporarily stops the counting.
Overall, the implementation of a 7-segment display circuit, the concept of decoders, and the concept of counters were effectively adopted. The use of synchronous counters showed the concept of flip-flops, where a number of flip-flops were cascaded together and clock pauses were implemented to the flip-flops simultaneously. The 99-second timer or stopwatch was simulated in Multisim and it satisfies the condition of a 7-segment display circuit. It completes a cycle of mod 10 counter that counts from 0 to 99 and then resets back to 0. The switch successfully carried out the functions of preset, pause, and reversing the counting direction of the timer or stopwatch. Furthermore, the circuit can be further improved by adding a minute and a millisecond display for the timer. An alarm could also be incorporated in the timer that will sound when the timer hits 0 or when a specific time frame has passed. And that would be all. Thank you.